Welcome to the KuppingerCole Analyst Chat. I'm your host. My name is Matthias. I'm lead advisor and senior analyst at KuppingerCole Analysts. My guest today is Alexei Balaganski. He is lead advisor in cybersecurity with a strong background in math, and this is something we might need today. Hi, Alexei.
Hello, Matthias. Thanks for having me again.
Yeah, great to have you again. And this is really something that I'm looking forward to because we are dipping our toes for the first time in a new topic that we have not yet covered before. We want to talk about encryption in general, and we want to talk about homomorphic encryption. And when you mentioned that this is an interesting topic that we could cover within our podcast, what I, as a moderator, would usually do, and I did that, to Google that term. And I came to a few introductory articles in publications around the web. And I checked back with you and I said, is this what you mean? And you said, no, exactly not, because there's much more about that. But before we start, Alexei, let's have a short look at encryption in general. What are the typical areas where encryption is applied? Where can we see encryption today, right now?
Well, Matthias, you're absolutely right. We have to start a little bit from afar. And normally when we are talking about encryption in various business applications, we are talking about encryption at rest, encryption in transit, and encryption in use. Well, the former two are pretty obvious. We have already figured them out for decades. So, for example, when we're talking about encryption at rest, we are basically talking about files or maybe database tables or the whole disks or partitions statically encrypted, if you will. You have a block of data, you have an encryption key, you apply the encryption once, and then it just remains like that until you actually need to access the data. This is encryption at rest. Pretty simple. Encryption in transit is for transmitting the data securely over a network channel. So if you want to move your data from one server to another, you have to encrypt it. And again, this has been figured out for decades. We have the TLS protocol, a standard for encrypting data on the fly, if you will. And it's usually the last one, the encryption in use, where it comes to confused looks and head scratches, like how is it even supposed to work? If you have your data encrypted, it usually means that nobody can do anything with your data. That's the whole point of encryption, right? And yet you are supposed to be able to use it somehow without decryption. Well, to tell you the truth, most companies which promise encryption in use, quote unquote, cheat a little bit. They do decrypt the data, but only the necessary part, and usually only within a secured hardware-based enclave where special hardware like secure chips or specialized processors ensure that nobody else can peek into your data while it's being decrypted, processed, and re-encrypted again, right? That's the traditional approach. This is what we use in database engines and so on.
And this is something that we would expect to have happened, because if we want to use the data, if we want to filter, if we want to process it, if we want to derive any information from this formally encrypted information, we need to have it in a form that we can have a look at it. So I would assume usually that even encrypted data that is stored encrypted, that is transferred encrypted, needs to be made available in the memory of the computer that actually these tasks can be executed. And this is changing right now?
Well, this is exactly how we expect it to work. And this is how most existing data processing solutions are implemented, as I mentioned, like relational databases, for example, because you have to keep the data somewhere in memory for heavy computational processing. Unfortunately, there are pretty important use cases where it just doesn't work at all. A typical example would be the so-called secure multi-party computation. A simple example, imagine like I have a pot of gold and you have a pot of gold at your home, and you want to find out who has more gold. But I'm not allowed to tell you how much I have, and so do you. How do we find out who has more money or whatever sensitive resource? A typical approach would be to choose a third party whom we trust and show them our gold pots, right? And then they would say, okay, yeah, Matthias has more. But sometimes it just doesn't work. For whatever security or compliance reasons, you are not allowed to show your unprotected data to anyone. And there are indeed cryptographical methods to perform this multi-party computation in a way that no party would ever reveal their data to the other party, and yet the computation will succeed. I am not even going to dive into the mathematical details of this approach, but just trust me, algorithms like this exist, and they have existed for decades. And they find pretty important use cases in like financial industries, where, for example, you have your salary data, and you want to invite an insurance company, and they need to know how much salary your employees have, but you cannot share that data because it's sensitive. And you would set up a special encrypted infrastructure that would generate a lot of cryptographic operations, exchange lots of data. It's pretty computationally heavy, but in the end, you will have your result computed securely and privately. And the same, in a way, applies to this homomorphic encryption. The idea is that you have your data encrypted, you apply some sequence of mathematical operations to the encrypted data directly, and in the result, you will have your computed result in the encrypted form. So whenever someone comes with an encryption key, they will decrypt your result, and it will be the real proper mathematical result of your computation. And no data will be decrypted at any time until it's actually needed. Sounds like magic, but it does work in a way.
Okay, if I get it right, so both the data and the processing remain confidential, but nevertheless, the results that we want to achieve can be achieved without at any time breaking the security, right?
Exactly. This sounds like totally counterintuitive, but it does work. And in fact, the first developments in this area have started in like 1970s, so like 50 years ago. And I would say within the last decade, they have reached the stage where almost any kind of computation can be performed in this homomorphic, always encrypted method. The problem is that in order to implement encryption in this homomorphic way, you have to first design basically an entire new class of encryption methods and specially crafted operations on those encrypted data. For example, every type of encryption has this property which is called malleability. Basically, again, without going into details, it means that suppose you have a block of encrypted data which says, for example, I owe Matthias 100 euro. And you take my encrypted data and you manipulate it directly without decrypting. And in the end, you will get the resulting text which says, I owe Matthias 200 euros. This is a well-known problem in the field of proper quote-unquote traditional cryptography, because you are supposed to detect and prevent these types of attack, right? You do not want your encrypted data to be manipulated. But within homomorphic encryption, it's actually a desired property, and you can design your encryption method in a way that it can be malleable into a specific way so that it allows performing a certain type of operation. For example, you can create an encryption method where two encrypted numbers can be summed, and the result of that operation would be actually the sum of those original numbers encrypted. So you can add two numbers without actually decrypting them first. The same would apply to other types of operation, multiplication, subtraction, and so on. And it took the scientists and mathematicians decades, from early 70s to like 2015, to design a set of methods to actually perform nearly any kind of operation on encrypted data. So nowadays, starting from 2015 or something, you have existing open source libraries, SDKs, and projects which will allow you to perform various operations on your encrypted data without decryption. There is only one problem. It's hugely computationally expensive. There is a lot of overhead where you have to encrypt, decrypt, re-encrypt different types of data. You have to exchange a lot of data over the network. It involves probably thousands of cryptographic operations for performing just one addition of two numbers. I've read some interesting research papers, and they would claim that if the result of a primitive operation took like several hours, it was a great achievement. And the same operations you would probably do in seconds if you were dealing with unencrypted data. So it is complicated, it is extremely performance heavy, but with the power of the cloud, it's actually already usable.
Okay, this is understood from my side, but when you say, okay, the technology is there, the mathematical foundations are there, but it has these limitations as you've described, what are use cases where this can really already make sense for organizations? Where could we see that in the near future actually showing up in our real life?
Well, the most obvious use case probably would be a financial industry, where you have to perform whereas relatively light mathematical operations, because when you don't have to integrate your money, you just sum or subtract or whatever, divide. But when you are dealing with financial records, you have to keep them safe. You have to keep them private at all times, right? So if you could perform your financial transactions using homomorphic encryption, that would be a huge improvement in compliance and security. And until a certain number of operations per second, I guess the computing overhead is okay. And there are already banks or insurance companies which are working on such projects. It's probably far from production use, but there are some interesting developments. And companies like IBM and Microsoft and other large cloud vendors, they have different libraries and SDKs, as I mentioned, and even cloud services which facilitate this implementations. Another interesting potential use case is, oddly enough, machine learning, because machine learning requires huge amounts of data for training, and the data is usually extremely sensitive. If only a company would be able to encrypt that sensitive data, let's say an automotive company collects usage data from their vehicles, contains lots of sensitive information about their customers, location data, again, financial records and stuff like that. If you put all that in a traditionally encrypted data lake or data warehouse in the cloud, you cannot do much. You could probably run some primitive reporting every now and then, but it's nothing even close to real time. But if you implement it on a large scale homomorphic encryption solution, you might have a lot of interesting real time insights from the data.
Right. So this homomorphic encryption would then actually be the key to actually have data privacy being established while being able of processing the data in a meaningful manner and in a compliant manner, right?
Exactly. To think of it, every solution for like data privacy enhancement we have until now are basically crutches. They are workarounds, like compliance checkboxes, if you will. So yeah, we have our data encrypted, but when we run an analysis for our business report, we have to decrypt it. Or when we train our machine learning model, we have to decrypt it. So yeah, it's like almost private. It's almost secure. With homomorphic encryption, it can actually stay encrypted all the time. So this is, in theory, the only end-to-end 100% secure and compliant method of dealing with sensitive data. So companies who need this kind of like 100% compliance, they are happy to jump on the bandwagon. The only question is like, why is it not as popular as, let's say, machine learning or blockchain or any other recent disruptive technology?
If we look at the use cases that you've mentioned and the question that you just raised regarding the popularity, are we not yet that far, or what is actually the reason? You've mentioned IBM and Microsoft and other companies being already some pioneers in this area, providing actual current tangible solutions. Should we expect that to be more popular in the future? Will that be something that we will see much more frequently?
Well, I see several of explanations why it has not yet gained the same amount of hype as other technologies. First and foremost, it's really, really complicated. From the computation, from the mathematical point of view, it's more complicated than machine learning or all those blockchains and stuff like that. requires a lot of investment into network and computing infrastructure, high performance infrastructure, and of course a lot of understanding how this whole mathematics works. You cannot buy it as a service, not yet at least. For example, if you want to utilize a machine learning method for image recognition, you already have like a cloud-based API which you just unlock with a credit card, and you can utilize it without even knowing how machine learning works. With homomorphic encryption, it's not there yet. You have to understand how it works. You have to build directly into your application business logic. And yes, companies like IBM or Microsoft or some other vendors, they do offer some level of abstraction with libraries and SDKs, but it's nowhere near that SaaS level yet.
So what you've shared today is an insight into your ongoing research. From the status that you've just described, this is something that is not yet something that shows up immediately in our current research, but we are nevertheless following that topic. Am I right?
We are absolutely following that. And I have to confess, the idea, like, why should we discuss it today, came to me after I've listened to one of the webinars from the IBM Homomorphic Encryption group. And there was a lot of interesting academic level of discussion. And again, so even though I do actually have a degree in mathematics and I try to read through their research papers and lots of fascinating research, it's a little bit over my pay grade, if you will, to understand how it works. But even then, I still have a feeling that while they have these amazing academic achievements, they still haven't figured out yet how to actually properly sell it to customers. Because customers just don't understand homomorphic encryption. It sounds too complicated. They would understand if it would be sold as a service, solving a specific use case that we have discussed earlier. We are not that far yet. I guess the same applies, for example, to quantum computing. You can already start using it today, but it's a little bit complicated. It's a little bit higher in complexity than a traditional developer or business user would expect to even understand what it does and what it cannot do. And this is probably where we as analysts can actually help those vendors. If we could explain homomorphic encryption to a person like they are 5, that alone would help to understand where it can be applied and how much effort is needed for that.
Right, and I think that is actually the value that we can provide as analysts, being the translator, translating between the technology and the business use case with the vendors. So for today, thank you very much, Alexei, for giving that brief introduction into homomorphic encryption. We will surely follow up on that quite soon because there is more to learn about. And the next question that I will ask, or the first question that I will ask in our next episode around that topic is why it is called homomorphic encryption and why homomorphic is the right term here to apply. But this is something for next time. Thank you very much, Alexei, for being my guest today.
Well, thank you, Matthias, and see you soon, sometime later.
Absolutely. Thank you very much. And looking forward to learning more about this really incredible innovation that we have here right now. Thanks again, and bye-bye.
Goodbye.